Hello, I'm Lee. In this video, we are going to explore the binary search tree operations. Let's start by building one. So how about let's assume the data we added to the binary search tree are just simple integers. So let's start by insert number 60 there. Let's see. So I'll have a node, and this node contains 60. All right, and now I'm trying to add 40 to the tree. So when 40 come in, so I'm going to compare 40 with 60. That means 40 is less than it, so that's going to go to the left to maintain the binary search tree property. Remember, the left subtree needs to be less than the root, and the right subtree needs to be greater than the root. So now if I'm trying to add 80, I come here, and that's the root 60. I'm going to go right and add 80 there. And now if I'm trying to add 50, let's come down here. That's a root. 50 is less than 60, so we are going left. Then we compare 50 with 40, this root. So this root for this subtree. And it's greater than 40, so we are going to go right. So we add 50 here. So now let's see, I'm trying to add 30. So come in, starting from the root, we do the comparison with the root item, and it's less than root, so we go to the left tree. Then we do the same operation for this current root, for this subtree. So 30 is less than 40, so we go left and add 30 there. Alright, now let's try to add 90. So the similar operation here, you come down, compare the root. 90 is greater than 60, so you go right and come down to this root of this current subtree. So 90 is greater than 80, so you go right again. Alright, now I'm trying to add 70. So come here, compare 70 with 60. Greater than, so go right, compare 70 with 80, so now we need to go left. Alright, now let's double check if this is a legal binary search tree. So let's start with this root. So the left subtree should be less than 60. That's true. And the right subtree should be greater than 60. That's true. Now examine this root. So the left subtree should be less than 40. That's true. And similarly, you can examine the other one. So the property of this binary search tree is maintained. So by looking at this add algorithm, this is what happened. We come to the root, we do the comparison, we decide, do we want to go to the left subtree or right subtree? Then we do very similar operations. And another observation will be, we always add a new node as a leaf. You see, we first did 60, then we did 40. We always add it as a leaf. So now if I'm trying to add 100, I'm going to come here, go right, and add 100 there. So that's an add operation. And now let's take a look at the search operation. Okay, it's called a binary search tree, so it must do something good about search. So how about if I'm trying to search for 30, so the algorithm, very similar, you come here, so compare 30 with 60, then you go left. The good news is you forget about the whole right subtree. So this one comparison cut half of the tree. So you only go left, then you compare 30 with 40. Again, you cut half of the right tree for this subtree and come down here. Then you compare and say, oh, I found the match, so 30 is here. So you see with 3 comparisons, you find 30 here. Now how about let's try to do another example. I'm trying to find 120. So you come here and go right and forget about the whole left tree. Come here, go right, come here, go right. That's where you hit the bottom, because the right subtree now is null, so it's an empty tree. You have nothing, and that you get the conclusion 120 isn't in this tree. So that's for retrieve operation. So we just take a look at add and retrieve. Now let's think about how to traverse this tree. For example, if I want to display every item in this tree and I want to display it in sorted order, now let's think about how are we going to traverse this tree so that we got a sorted order of data get displayed. Alright, now let's think about when you see 60, do you want to display 60 now if it's sorted order? Maybe not. You want to display the left subtree first because they're less than 60. Then you display 60, then the right subtree. Alright, so we break it down. We say when you try to display this tree rooted at 60, the algorithm will be first display the left subtree rooted at 40, then display 60, then display the right subtree rooted at 80. Alright, so when you're trying to display the left subtree, now let's think about, okay, similarly, you don't want to display 40 first. You want to display the left subtree first, which is 30, rooted at 30, then this 40, then the right subtree. Alright, now we're getting somewhere. So now when you look at this subtree contains 30 and the left empty tree and the right empty tree. So again you say, oh, I want to display my left tree first, but it's an empty tree, so there's no operation there. And then you display 30, then you display the right subtree, which is empty now. So after you're done with this subtree, you should display this 40, then you display this subtree. Now you come to display this tree rooted at 60. Now it's time to display the right subtree. When you display the right subtree, when you look at this subtree, and so you're going to think about, oh, I want to display the left tree first, then the root, then the right. Alright, so that comes our in-order traverse. It's called in-order traverse because that gave you a sorted order. So pretty much when you do in-order traverse, you first traverse the left tree, then it's a tree, traverse the left tree, so you got 30, 40, 50, 60, 70, 80, 90. So that's an in-order traverse. Now let's think about when do you want to use in-order traverse? Of course, when you want to display it in order, when you want to traverse it in order, in sorted order, by certain key, by the key you use to build this tree. Alright, how about this? Another kind of traverse is called a pre-order. Pre-order says I'm going to display root first. Then it doesn't have to be display. I'm going to process this root data first. Then I'm going to process this left tree, then the right tree. So that's the idea of pre-order. Do the root first, then left tree, then right tree, in that order. Okay, and now you think about this. So when you think about root, okay, process 60, then left tree, okay, left tree itself is a subtree, so you do the root first, 40, then left tree, 30, then right tree, 50. So after you're done with this one, it's time for this right tree because it's pre-order. You already done 60, left tree, right tree. When you do the right tree again, you're going to do the root first, 80, then 70, 90. So if we do a pre-order traverse, that will be 60, 40, 30, 50, then 80, 70, 90. So that's pre-order traverse. So let's think about in what scenario you might want to do a pre-order traverse. Let's think about, what if I want to copy this tree? I want to make a copy of this tree. And it makes sense to copy the root first, then the left tree, then the right tree. Okay, so that's a typical usage of a pre-order traverse when you want to build another tree, okay, based on this tree. Alright, as you might guess, like we have another order traverse called post order. So post order is the opposite of pre-order. So you do left tree first, the right tree next, then the root. So left, right, root. Okay, and so let's say, for example, for this tree, we're going to left, right, root. So when you do left, that will be left, right, root. Okay, and when you do right tree, left, right, root. So when you do a post order traverse, what we got is 30, 50, 40. So that's a left tree for this root, and then right tree 70, 90, 80. Okay, after you're done with this right tree, and you can do 60. So that's an order for post traverse, for post order traverse. Okay, so now let's think about when you might want to use post order traverse. So think of the other line. When we build a tree, we want to build the root first, like when you make a copy of a tree. So now think about when you want to destroy the tree. Destroy a tree, do you want to destroy root first? If you do destroy root first, then you lost track of your left tree and the right tree. So obviously in this scenario, you want to delete the subtrees first before you delete the root. So this is a typical usage of post traverse: delete left tree, right tree, then the root. So that's how you destroy the tree. So now we finished looking at the traversing, 3 different kind of traversing for binary search tree: in order, pre-order, and post order. Now let's take a look at the last operation, how to remove something from a binary search tree. So now let's take a look. How about when I do remove, let's try an easy one first. If I want to remove this node 30, so if I want to remove node 30, that's easy. So remove. Okay, you can imagine, just set this pointer to no. Then this tree is this node is gone. So as a leaf, it's very easy to remove a leaf because you just set the pointer to no. That's all. Delete this node. That's all. You don't bother the rest of the tree. You're just a leaf. Okay. And now let's take a look at how about now if I want to remove 40. So if I want to remove 40 at this moment, because 30 is gone, so 40 only have one right child. So if I want to remove 40, that's still easy. So you want to remove 40 and 50 can replace 40 here. So you just replace this 40 with 50. So this one just take place of the parent. So 40 will come here. So let's take a look. So 40 will come here, and this is gone. So you just set the right tree as no. That's gone. So one we just did removing a leaf. That's easy, and removing a node with one child. That's kind of easy too, because you just say this child will becomes a parent. That's all, and set the only child pointer as no. That's it. Okay, now let's see if I'm trying to remove 60 here. So here's the objective. I want to remove this guy. And what's special about this guy is it has 2 children. So when you leave, it's easy. When you only have one child, it's still easy. Just let your child take your place. And when you have 2 children, what do you do? When we remove this one, how about this tree? So it's kind of very destructive now if you remove this node with both children there. So now let's think about what can we do about this tree and how to remove it. So how about let's start from beginning. So that's okay, let's draw this one. So how about let's say 60. Let's restore the original tree so that we can draw on it. And 30 and 50. 80. 70 and 90. Okay, and now my objective is to remove this guy, and we realize remove this node will do some damage for this tree. So now let's think about removing a leaf or a one child parent will be much easier. So how about let's think about this. How about we're trying to swap this data with a leaf or a node with just one child. That way, after the swapping, we can we can just delete that easier to delete node. So the idea, now let's take a look at this 60. Anyway, this 60 will be gone. So first think about this. Which data do I want to move up to this node, to this root? Which data do I want to move it up so that this tree still maintains the legal binary search tree property? So when you think about this, 60, who's next to 60? So if you do it in order traverse, who's next to 60? So now that comes down to this 70. So now let's think about how about if I put 70 here. So here's our strategy. I put 70 here. So I don't delete 70, but when I put 70 here, overwrite 60 with 70, this is a legal tree, and this 70 anyway, we can delete it. So that's the idea of deleting a node with two children. When you delete a node with two children, think about pick one to replace you at this node, because this node is hard to delete. So pick one to replace you so that the tree is still a legal binary search tree. And when you pick one to replace you, you want to pick an easy one. So which easy one? The one right next to you. The one right next to you will still maintain the binary search tree property here. And which node will be the one right next to you? So let's think. If it's next to you, you have to go right. If you go right, then you have to go all the way to the left. You have to go all the way to the left to do that. So that comes to 70. Because you have to go all the way to the left to make sure that's the data immediately next to you. Go all the way to the left. That can make sure that's a node that doesn't have two children. So think about this. If 70 could be a leaf. In our case, this one is a leaf, so it's easy. You just get rid of it. In another scenario, if 70 have a right child like 75, that's still okay. 70 is your in order successor. So you move up 70, delete 70, 75 take place of 70. So that's our strategy of deleting a node with both children. So you'll find the in order successor. That's a node you want to swap with. So you put the data of your in order successor in this node and trying to delete the in order successor. One thing for sure, this in order successor will be either a leaf or has only one child. Otherwise, it couldn't be your in-order successor. And how to find your in-order successor? You go right, then go all the way to the left. That guarantee you to get to your in-order successor. So that's the algorithm for delete. Thank you.